to physical chemistry and thermodynamic studies of solutions, electrochemistry, colloids, and interface. Professor has various research collaborations with Germany, South Africa, Tunisia, CSIR labs, and NITs in India. He is a member of several professional, scientific, and academic bodies in India and delivered more than 35 lectures in various colleges, universities, and IITs in the last 5 years. He has supervised 17 doctoral students and published more than 250 research articles in various reputed international journals with 3,200 citations and H-index 11. Once again, I am very happy to invite Dr. Amalendu Pal sir for his lectures on ionic liquids. Now I would like to hand over to Dr. Amalendu Pal sir. Sir, please.
Okay, thank you, madam, for your brief introduction.
Thank you, sir.
Good afternoon to all of you. My topics last time it was in fact green solvent for the future. Little bit I have to show some of the slide left, few slides. That is very interesting. That's why after that we'll start with the ionic liquid. Okay. So some of the slide we missed last time. I am going to that slide first. Then we will go very interesting topics on ionic liquids. Okay. Because application of green chemistry to tell that I told you green chemistry not a solution to all environmental problems, but the most fundamental approach to preventing pollution. And now we have to green approaches lab. It's either in PG lab, either in UG lab. Some of the example I will show that we can put in our syllabus. So some of the example, I have used examples for green approach in lab. This thing we have discussed, that is acetylation of aniline. We have used acetic anhydride, pyridine, and chloroform. I told you this is not a green solvent. Acetic anhydride, pyridine, and chloroform chlorinated compound. So these three compounds not eco-friendly. That's the most green way. I told you acetic acid, take zinc dust and boil, then you can get acetanilide, because acetic anhydride, most of the state I think banned for use. So that is also minimum waste product, avoid hazardous substances. This is the best way we can do. We can use this in undergraduate level practicals. Next I'm coming, that is the photochemical reaction, PG level we can do. We have 5 PG level green chemistry in lab, but although just I am showing one only, that is benzophenol that we can prepare from benzophenone in the presence of sunlight, and isopropanol as an reducing agent in presence of acetic acid. And that acetic acid we use in order to prevent the cleavage of benzophenol. If it is cleavage, then it will come to the benzophenol. That's why you have to use the glacial acetic acids. Okay, that is the benzophenol we can prepare just photochemically in presence of isopropanol and glacial acetic acid. These chemicals are very safe, safer reaction condition, you can say. And we are using also renewable source of energy, that is H nu solar energy. And this final product, benzophenol, this is the final product that we can use for our next experiment. That is, let's see, that is the pinacolone reagent. Benzophenol we can prepare in previous slide that way. Then we can put some iodine and glacial heat, and 5 minutes that you can get benzophenol. That is so. This is the pinacolone rearrangement. So we can get pinacol to benzophenol. So this is the simplest way, green way we can prepare benzophenol than benzophenol. This is the safest method I can tell you that we can introduce in our PG level. Another example that I told you before, not necessary to say here. Now we are coming. That is base catalyzed aldol condensation. Undergraduate level we can do also here acid, benzaldehyde, acetone, sodium hydroxide ethanol, then we can prepare dibenzyl propanone. That is no, there are no hazardous solvents here. Reagent are also non-toxic. That's why this experiment can be introduced in undergraduate levels. So another example I'm talking, that is cycloaddition reaction undergraduate level we can introduce just simply furan and malic acid. Just a minute. Furan and malic acid. Benzene and reflux. Benzene, I told you most of the time, it is a very, very toxic solvent. So this technique, this method is not good in that sense, because use of benzene, which one of the most toxic solvent. So we have to avoid as much as possible benzene in our lab. That is the green procedure I'm telling. Simply you take this furan and malic acid, then water, room temperature, then reaction in aqueous media you can do, and also at room temperature, and also atom efficiency 100%. जितना atom layer reactant में उतना atom product में आ गया, no byproduct. So this is the experiment, simple experiment we can introduce in our undergraduate levels, although it is JACME published in 1980 and 1948. So 1980 journals you can see also. So another things, that is the nitration of electrophilic aromatic substitution reaction. Phenol, sodium nitrite, sulfuric acid we are giving. Nitration, PG level we can introduce, but this one is not greenish way, because we are using the concentrated sulfuric acid. Is not good to use in concentrated sulfuric acid. If you talk about the green solvent, that is alternate green procedure, you can use calcium nitrate and acetic acid. Nitration also is very rapid and eco-friendly nitration, nitration of phenol and its derivative also, and byproduct is calcium acetate here. So calcium acetate you can use for the agrochemicals. So we can say it is environmentally benign and also eco-friendly. This one is the green procedure we can introduce in our TG level. That is the electrophilic aromatic substitution reaction. Another ones also, another example I have put it here, that is electrophilic aromatic substitution reaction. That is bromination of acetinolide. You see the here also we are using bromine mostly, because I told you bromine is very toxic and also corrosive. Here liquid molecular bromine we are using here. We have to avoid that things. That's why we are alternating green procedure that we can introduce. That is the seric ammonium nitrate, caviar, water, and ethanol. That is the solvent also is greener solvent also, but not bromine. In place of bromine, we are using this four. So we are replacing corrosive bromine. So we have to avoid that things, and also we are avoided also acetic acid also. Although acetic acid can possible to use also rather bromine. So I'm telling this thing, bromine is dangerous. I'm telling organic people who are working maybe knowing about that things. I told you last time that someone happened as a problem came in our pharmaceutical labs. So this reaction can be bromo-derivative acetanolide. If you want to make reacts identification organic compound, even UG and PG level, you can introduce this one. Another ones, this one, that is the bromination of chalcone. Here we are not using bromine. You see the situation, tetrabutyl ammonium tribromide and water, and 15 minutes you can boil it. And this is bromination here, 95% product, and also highly toxic hazardous liquid bromine, corrosive chemicals, bromine, toxic hazardous, and corrosive also. This is we are avoiding for bromination. That papers of the tetrahedral later 1998 2001 also they are known to us, although they are organic chemists anyway. And now we are coming a little bit. Some of the examples I have used example that can be introduced in our syllabus in PG as well as UG levels, if possible. That is the problem is that to take the initiative, who will do these things? That is the most because monotonous. That should not be. We have to take initiative. That's very important. Anyway, that is the policy matter of the government itself. I think even syllabus change also university itself. So anyway, preparation of ionic liquid. This is very, very simple. We are preparing in our lab such type of ionic liquids. That is, you have pentyl bromide. This is the 3-methyl imidazole. This is 3-methyl imidazole. We'll talk about details about that things. And this is pentyl bromide. This is a simple procedure in lab you can prepare. That is 1-pentyl 3-methyl imidazolium bromide. So this is the compound we are preparing ionic liquid. Why we are preparing this ionic liquid? So this is 2002. This is a simple ionic liquid. This is easy to prepare in lab itself. So these ionic liquid we can use as a catalyst. 1-pentyl 3-methyl imidazolium bromide for next reaction. You see, that is 2-phenylbenzothiazole. This is 2-phenylbenzothiazole. Here ionic liquid acts as a catalyst. Okay. You can that ionic liquid act as a catalyst. This ionic liquid you can recover also. So you can getting the product as well as that is no byproduct. Only the catalyst remain in the reaction mixture. You can recover it. So these ionic liquids is benign, work here as catalyst as well as reaction media. That's why no other solvent is required in this reaction. And also this reaction is also atom efficient. जितने atom ले उतने atom product में आ गया. So that is the main worker is Bindamun B. Sirano, Bindamun Rano in Jadupurin cultivation of science. Anyway, chemical later that papers also they are details. The procedural step, how much amount, how much reaction time, that procedural step you can get it. Although I have all these things, even that in this paper you can get it details of preparations, details. So just I'm showing the application point of view in our lab. Now we are coming a little bit deviation of that things, what we do in our lab, organic qualitative analysis. We are doing this thing in our lab still today. What's the problem we are facing? We are using the metallic sodium with fusion with organic compound is terribly hazardous, is a cause of great concern in a student laboratory. My experience when I'm telling it is more than 10 years back. I was in the lab sitting room. After 5 o'clock, everybody left in the departments. Then all of a sudden, some people coming from the roadside. That is a burning in the lab in top floors. How it is happened? I'm telling these things. It is a after 5 lab attendants take all the materials and put in the dustbin, no, put in the basin itself, and that sodium is there. Then it becomes burnt, and it is a trivial burning situation. We have to call the fire brigade also. I'm telling this thing. That situation is horrible at that day. I remember very much. That's why we have to avoid the metallic sodium, because lab attendant does not know what is the important, what is the problem with the metallic sodium. That's how we have to find alternate. That alternate I will tell you what we do. Then for the nitrogen sulfur halide detection के लिए we use sodium. So we have to safer procedure or non-hazardous procedure or green procedure we have to use instead of So metallic sodium, we can use zinc sodium carbonate and this powder. Just red hot, it red hot it automation take if it's more so I now you can solve you do you in the yeah. So this is uh, uh, not 5 ml, approximately 5 ml. Uh, uh, well, just we take the we and we rest oil that nitrogen for things that we are doing in our lab for the nitrogen, sulfur, and halides. Even filtered, you can figure cool and bromine and iodine. Well, then if it includes ammonia, then this is the you are also discussing, and that's why we have to avoid sodium. Instead of that, we can use zinc and sodium carbonate. This carry the same experiment used today. So that so and you can the big good way you can uh, organic analysis. The people who are in inorganic background, I have to focus to them what we are doing. Is the identity and so my suggestion is that you analyze that. Okay, the analysis when carbon and and carbon. So it takes what we are discussing about the inorganic analysis, we have to identify first anion, then we have to identify cation first. And we have to take sodium carbonate extract with the mixtures, and we have to take the filtrate. We have to take the filtrate, and that filtrate mostly anion. Residue 50% mixture will go to the cation part. So present proposal is that cation analysis, we have to take the residue from the sodium carbonate extract, and from residue part that may be copper, arsenic, antimony may be present. So in that case, that can be tested. That take 1/4 of the sodium mixture, neutralize its slight excess or dilute excess, then pass H2S. Then you can copper sulfide, antimony sulfide, arsenic sulfide. You can get different color. You can say confirmatory trace. So if any precipitate not appear, then we can say copper, arsenic, antimony absent. Okay. So another things also, this is the same thing that I told you before. This is also same thing. Some of the compound you cannot do covalently bound nitrogen, aromatic compound, that is para-nitrophenol, para-aminophenol, nitrogen testing you cannot do with this. The you can take few milligram of compound, twice the quantity of sodium potassium salt of any, that is sodium acetate or sodium oxalate or sodium succinate or sodium benzoate. You take, and with the mixture you ignite it in a tube, and then from ignition you can take this one test. You can do test you can do for organic. So another thing is also qualitative inorganic analysis that I told you last time. It is better to do the spot test. Spot test is not so is easy in the sense because amount of, I'm telling, because you have to avoid sulfuric acid, nitric acid, hyaluronic acid. Because the laboratory also fail with all these acid vapor, which is not at all healthy atmosphere. So better to do how to do the spot test. You can get it any test book. Sometime we can do because double S, that is absorption spectroscopy, same photometers you can use also. What atomic absorption double S is so expensive instrument, that's why it is very difficult sometimes some remote area. But you can test all the metal ions. But the alkaline method, sodium, calcium, you can do with the fluid photometers. So the other thing is that you can introduce, and spot test you can see 6 gram microgram, that is sensitive. So traces amount of basic radical present is best method. We can say green procedure also. Now we are coming green solvent ionic liquid. Let's come. We'll go. Very interesting one because this will develop last 3 decades. Rather, we can say 2 decades. 2001 to ionic liquid. A lot of works still going on. I will time to time I will suggest who are in university level or undergraduate level, they can do some work with the ionic liquids, how to do that ionic liquids. I'm telling, there are a lot of vacant space to do research with the ionic liquids. So first we have to go through the basic things. I will not go to the research point of view, but what are the research going on? Recent years, chemical researchers, as well as industrialists also, I will tell you, are under pressure to replace many of the hazardous, toxic, flammable, volatile, VOC. Because I'm telling, we have to replace most of the organic chemicals. We have to use the ionic liquid in place of that. So that is the greener replacement for traditional volatile organic solvent in different field. Whether if you go to the chemical synthesis, catalytic chemistry, electrochemical device, separation technology, biomass degradation, because iron liquid it is characteristic physical properties that I will tell you a little bit. Some of the point I will touch, not details. Okay, what are iron liquid practically? These are materials that composed solely of organic cations and organic and inorganic cation. This is very, very important part. That is definition wise, not definition I can tell, but what are iron liquids? That is the organic cations and organic and inorganic cation. This is we have to remember these things. So if we say the definition of iron liquid and molten salt, but question again comes, a lot of things to tell. Sodium chloride is also molten salt, but sodium chloride is iron liquid. No, this is not an iron liquid. But iron liquid is a molten salt. But if sodium chloride is a molten salt, then sodium chloride is iron liquid? No, no, no. This is not that. Sodium chloride is not an iron liquid. So we are coming are defined as material containing only ionic species without any neutral molecule having a low melting point, less than 100 degrees the melting point, generally ionic liquid. What is discovery I'm telling little bit. Low melting point salt 1914. That is ethyl ammonium nitrate. Ethyl ammonium nitrate melting on 12 degrees. This is the first melting salt. At the time, salt not iron liquid top. First room temperature iron 1951. That is N-ethyl pyridinium bromide, aluminum chloride melt. These are the first room temperature. After 1931, there is no work on iron liquid, not progress. You see 1951 to 1982, there are a lot of gaps. First, most stable conductive salt came in 1982, that is 1,3-diethyl imidazolium salt in 1982. But after 1982, 10 years, 1992, no work with iron liquid. Nobody thinks about the iron liquid at that time. Practically, I can say hydrophobic iron liquid first came. That is the 1-ethyl methyl imidazolium tetrafluoride. It is 1992. When 1-ethyl 3-methyl imidazolium tetrafluoride came in 1992, after that long gap, again 10, we say 2000 or 2001 to then people think about the iron liquid. That is a very interesting one. That's they started after 2000 or 2001. Last 2 decades, huge work is going till today is going on. What is the feature of the iron liquid? That is solvent or open fluid at room temperature consists entirely of cation anion species. This is important because it is a peculiar physicochemical properties of the iron liquid because have no measurable vapor phases. So you can keep it longer period of time, open bottle in air because evaporation is not too much because vapor pressure is very low. Because not only that, it's boiling temperature at 300 degree minimum. So we can say usually non-flammable. I'm telling most of the organic solvent is flammable. Appreciable liquid range, high thermal stability -80 to 300 degree temperature it can stay. Tunable viscosity, electrochemical window, that is oxidation reduction. Tunable viscosity, that is the things I will tell you a little bit later on. Good solubility properties of a wide range of both polar, non-polar, inorganic, organic materials because most of the polar or non-polar materials, whether it is inorganic or whether it is organic, it can dissolve in iron liquids. This is very, very versatile solvent. Another thing, vast number of possible permutation. This is one what I'm telling, designer solvent. Why it is a designer solvent? We say possible permutation, what go bataunga, why it is a designer solvent, that you can understand in my talking, next talking. Let's see. This is traditional salt. If we say, if we an example of sodium chloride here that I'm showing. This is an ionic solid, molten salt, but it is not an ionic liquid. So that is high melting point, also 800 degree, whereas ionic liquid generally lower melting point, below 100. So traditionally, that structurally if we see, इसका जो सोडियम क्लोराइड जो है asymmetric anion and asymmetric cation, that arrangement is arrangement of the chloride is fixed. Asymmetric anion is there in ionic, but acidic cation arrangement is not uniform throughout the lattice in ionic liquid, but sodium chloride arrangement is uniform throughout the lattice. That is structurally sodium chloride and ionic liquid is totally different. So here I am writing cation asymmetrically substituted with different length group to prevent the packing of the cation anion. With this cation, that is not possible to packing, but sodium chloride is packed structure. So this needs to have an asymmetrical organic cation. Asymmetrical organic, this part, cation part is organic cation, and the anion part it must be organic, inorganic anion. So asymmetry is responsible for movement in ionic, but symmetric arrangement of cation in ionic solid sodium chloride is high melting point, 800 degree. So this is the, don't confuse all these things. What is, all liquids are ionic liquid? No, this is not. Like they're all molten salt are ionic liquid? No, this is not. Although ionic liquid is a molten salt. Let's have, so there is a need to develop more environmentally benign solvent or use solventless system. So ionic liquid should replace toxic, environmentally hazardous and volatile solvent. So necessary to develop optimized reaction condition, you use these solvent ionic liquid at the same time minimum amount of ionic liquid solvent we can use, we can get maximum yield and minimum energy loss. So that we have to very important, and that is user. That depends upon the use. Example include use of solid non-volatile liquid rather than volatile, flammable, environmental hazard organic compound. It is non-volatile ionic liquid, is solid liquid also, that I'm telling. So it is non-flammable, it is not hazardous, environmentally not hazardous ionic liquid, that is better one in place of VOC. Another, why consider ionic liquids? I told you ionic liquid is environmentally friendly alternative to organic solvent for liquid extraction. Because what is very meaningful liquid extraction, that is a separation, also separation technology is there. Huge work is going on separation technology. I will tell a little bit time to time. Catalysis, one example I have given to you earlier today at the beginning. Catalysis also, electrochemistry also. So ionic liquid will reduce, eliminate the related cost, disposal requirement if it is act as a catalyst, no disposal requirement. Hazardous associated with the volatile organic solvent, it is not so hazardous. So the ability to fine tune the properties of ionic liquid media, which allows selection of ionic to replace specific solvent in a variety of different processes. Meaning, after it is your purpose, what purpose you want to use the ionic liquid in place of the organic solvent, in place of the VOC. So that is you can fine tune. you can, you must be knowing the properties of the ionic liquid and purpose of the ionic liquid, what purpose you want to use that thing, or whether that ionic liquid is relevant to your purpose, that you have to know. Let's see, why consider ionic liquid as green solvent? This is a very characteristic properties, very good physical properties. It has low melting point. It has very low vapor pressures, 300-degree boiling point mostly, non-flammable, wide liquid range, thermal stability is very high, moderate to high viscosity. That I'm telling, viscosity is very high. Most of the ionic liquids, and I'm telling this field for the undergraduate level, teacher can do the viscosity measurement of ionic liquid. There is no lot of literature data of high viscosity of the viscosity of ionic liquids. So this is a good one to study simple way. एक ऑक्सफोर्ड विस्कोमीटर, आगोल विस्कोमीटर यूज करके एक बात cooling or heating system may you can measure series of ionic liquid viscosity. This one is very important nowadays. Viscosity data are not available. I'll tell you not only viscosity data, that is the toxicity behavior of the ionic liquid not available till today. I'm telling even refractive index data, dielectric constant data, 4-5 parameters not available in literature, which is very important, very significant. So some teachers in college level can do that things. Very simple method, very input cost is not too much. Few amount of money to invest. You set up a lab and bath, water bath, and viscometer, then you measure viscosity straight to different temperatures. So anyhow, solvent property is different from conventional molecular solvent. Good be bad hai, because that's why I'm telling the what purpose you are using the ionic liquid. If it is your purpose solved, then you can say it's good. If it is not solved, because most of the polar, non-polar solute dissolve in the ionic liquids. So this is very important. And solvent properties can be controlled by selection of anion cation. Anion cation means you can change cation, you can change anion. There are permutation way you can prepare ionic liquids. That's why we say designer solvent. This is very important word. Solubility is excellent. Most of the solute, polar or non-polar, can dissolve here. Catalytic activity is also very good. What is the characteristics? I'm telling what also very important. That is RTIL, because we are recently very much concentrating on the RTIL. Ionic liquid having melting point below the room temperature, called room temperature ionic liquid, IL ionic liquid. RTIL is also ionic liquid, but if the ionic liquid room temperature melting point below the room temperature, you can say RTIL, room temperature ionic liquid. This is very, some of the ionic liquid is very characteristic properties. Then that we say it is RTIL. এবং उसका melting point that is below the room temperatures. So another thing, better conductivity, better conductivity, good solubility, and antimicrobial activity also in ionic liquid. Nowadays, most of the biological peoples are working in the bacterial activity in ionic liquids. And unique catalytic properties, every topic I'm telling is very simple. A lot of work is going on because we are doing conductivity part, we are doing antimicrobial part, we are doing that things. Okay, applied in different field like lubricant, nanomaterial synthesis also is very good field to synthesize nanomaterials in ionic liquid media. Polymer industry is another field also. Pharmaceutical industry is another field also. Batteries also another that field we are working with the lithium ion battery. using inolipids. Electrochemistry also, this is part of that, although. Now we are coming, choice of cation anion determine physical properties that I told you. That is a permutation. You can change cation, you can change anion, and once you change it, then properties will change. Properties in the sense viscosity, density, water solubility, that will change. Cation generally big and bulky. I'm telling one slide. This is very, very important, big, bulky. I'll show you some of the cations. Asymmetry accounting for low melting point. Actually, it is a structure of the cation, mainly cation structure, determine the properties of the chemical or physical properties of the inolipids. So these are created by alkylation, amine, imidazole, pyridine, phosphine. There are 8 types of cation, 8 types. This is very, very important. 8 types of cation. So cation will determine the physical chemical properties of the inolipids. So anion contribute to the overall characteristics of inolipid, determine the air water stability. Anion is also, let's see what are the cation, what are the anions. This is the things I'm telling. Most commonly cation. There are 8 types of cations. Here I'm showing is only 4. 1, 2, 3, 4. Yes. There are next slide probably I have collected total 8 cation available till now. This is 1 alkyl, 1, 2, 3, 4, 5, 1 alkyl, 3 methyl imidazolium, and N alkyl pyridinium, theta alkyl ammonium, theta alkyl phosphonium. But I am telling these things till 10 years. I am telling this thing. We are working in imidazolium based inolipid. This one only. But why this one, not this 3? Because there is huge work pending with the imidazolium based ion. Another thing is also imidazolium based inolipid is more stable compound. If you prepare, you can stable. But this type of tetraalkyl ammonium is not so stable compound. It's not so easy to prepare. Tetraalkyl phosphonium also is not so easy to prepare. That's why we have choose 1 alkyl 3-methyl imidazolium for the stability point of view, and to prepare it is very easy. And permutation combination I'm telling here itself. You see 1 alkyl, this is alkyl part. This alkyl part methyl, butyl, hexyl, octyl, dodecyl. You can this part, you can change it. Once you change it, how many? If you take here, there are 5 alkyl chain. 5 alkyl chain you can put it here. I mean, you can get it 5. If it is 1 ethyl, 3 methyl, then 1 butyl, 3 ethyl, then 1 hexyl, 3 methyl, that 1 octyl, 3 methyl, and 1 dodecyl, 3 methyl imidazolium. But this is the 5. Again, I'm telling, if you take is ethyl here, but that methyl can be changed. That methyl may be ethyl. So that is the 1 octyl, 3 ethyl imidazolium. Permutation combination of therefore 1 butyl, 3 hexyl imidazolium. You see the permutation combination. So you see degenerate solvent, you can change whatever you want. Alkyl group आप change करके आप prepare कर सकता. So this is that the thing, and anions part, that is hexafluorophosphate, this trifluoro imine, and a lot of BF4, C3, that is also a soluble part. That is the property. Most of the alkyl part, if it is present here, then it is very soluble. So this is the thing, permutation compound. Next slide, I'm telling, I'm showing here cation here, but this is not. It is total 8. Yes, this is 4, 5, 6, 7. 7 I have shown it, but there is another also. Anyway, you see it is pyridinium cations, imidazolium cations. I have shown. I'm discussing that thing. Ammonium cation, pyrrolidinium cation, sulfonium cation, morpholinium cation, and pyridinium cation. So you see there are 70 cation, but don't know yet. So this is the cation part, and you can attach either bromine, either chlorine, either BF4, PFC. You can attach anywhere, any cation ke saath. You can attach all these. I have shown only some of the anion bond. That anion bond you can attach here. Okay, this is a total permutation. And permutation means you can attach bromine, you can attach chlorine. This way you can prepare, you can change R1, R2, you can change R1, R2, R3 imidazolium. That you can change it. Okay, but this is totally the purpose and also the property is also very important. But I'm telling these things. Mainly, we are doing this one, imidazolium cation, but not all other 7 cations. And we are changing more than you can say we are prepare more than in our lab more than 30 to 40 lipids. So you see the permutation combination, but it is our research problem. What type of problems? Just generally we choose the problem and we prepare the materials in lab and we characterize it. Then we can use it for our purpose or for our problems. But after that, we don't use 15 or 1 month, we throw it out. But these things is that accordingly we do these things. So you see that is a lot of work to do in this way. Anyway, another thing is also very interesting topic. Still, we are working presently surface active ionic liquid. You probably, I'm telling, you know the natural surfactant means SDS, sodium dodecyl sulfate, TTAF, CTAF, all these are natural surfactants. But surfactants, their natural surfactant properties, and if you take the ionolipids surfactant property is much higher than the natural surfactants. So this is very important talking. I'm telling ionolic also a surfactant, but uska jo surface activity ionolic is much higher than the natural surfactants like sodium, SDS, CTAP, TTAP. All these are CTAT. Uh, these are I'm telling here is also interesting in the sense there are different types of cell. एक है cationic, एक है anionic, एक है cationic surface active, एक है deuterionic surface active, एक है bioamphilic surface active anionic. There are 5 types of cell. 5 types of what type of cell? Let's see. If it is cation is larger than the anion, the chloride, because C12 means that is hexadecyl 1-methyl hexadecyl imidazolium chloride. But a cation part is larger than the anion part. That's why we say cationic surface active liquid. Another thing, C4 means 1-butyl 3-methyl imidazolium dodecyl sulfate. Here DS anion part larger than the C4 mean cation part. This one is larger than the C4 mean. That's why we say anionic surface active ionic liquid. Ever cationic surface active liquid means दोनों ही same size, means C8 mean C8OSO3 दोनों ही same size. That's why we say cationic surface active ionic liquid. Another thing, deuterionic surface active ionic liquids. That is both the ions have the same molecules. This is the N-alkyl N' carboxymethyl imidazolium salt. This is that. Another salt, it is biamphiphilic surface active ionic liquid. Here, I am unable to show the structure because I have the structure, but not necessary just to name, you remember. So the alkyl chain is introduced in both positive and negative type head group. That was first again came in 2012 by Villa in chemistry journals. That is benzyl N-hexadecyl trimethyl ammonium dioctyl sulfosuccinate. So VSDOT. That type of surface cell, surface active ionization came in very recent 2012. You see what is going on. But I'm telling mostly what we are working cationic and anionic surface. We the two types surface active ionization in our research area at present. But we are using deuterionic also. We are using also Gemini surfactants also. Little bit, little bit. Anyway, these are the things. Now we are coming, that is 1-alkyl trimethyl imidazolium is the most common cation. We are using imidazolium cation. I told you this is most stable compound and stability is very high and if the impurity is so high, not too much. You can purify very easily. That's how we choose this one, imidazolium cation. Ionic non-volatile thermal fluid, hydraulic fluid, high temperature, low temperature lubricants, technological application. Another thing, electrochemical cell, lithium metal, lithium ion batteries. This part we are working, that is lithium ion batteries nowadays. This is with ionoliquid media. That is electrochemical. वो LED आजकल बहुत ज़्यादा चल रहा है. Ionoliquid sensor also, fuel cell membrane also. Another thing, even organic reaction में ionoliquid use as media. Hydrogenation के लिए ionoliquid media, hydroformylation, epoxidation, free radical reaction, alkylation. Some of the examples: Sonio, dialsol reaction, Hague reaction, Kaplan reaction. These are the some of the reaction I'm telling. You can get it all these things. जे किस तरह का ion liquid यहाँ use हो रहा, but it is using ion liquid as a media for reactions. Application of RTIL, that is one word. Some of the things very difficult. This is a first subject. This is wide range of possible application in ion liquid can be used to our advantage. For example, as reaction media, it is common in chemical process. The process chemical separation process. Separation process means I'm telling it is a separation technology. Big technology is going on by using ion liquid. I'm telling one example. I have been in Germany for 2 months, and there are by mentor. He is head although of the department, but he is also CEO from separation technology lab. It is the same city and 24 critical industry lab. The thing is that why you are favoring algae, why sometimes you favor mark, why we are very fond of, because purity is very important. Purity is very important, and they are spending money for purity of the chemicals. They are preparing the chemicals, of course, but they are facing the problem purity. They are want to, we get it 99%, 99.9%, but same chemical you can get from other chemical industry, maybe 98 or 97%. But what's the problem? 97 for research purpose. I'm telling we don't prefer uh, 3% then and water content or something like that, other impurities. But problem is that we need 99% pure chemicals. Why you are fond to buy from LPs, either Denmark, Germany, because they have R&D is very strong. Separation technology, they are set up the lab, they are coming to the lab, that lab, they are giving the chemicals, they are telling that we are purifying up to 98%, but we need 99%. So how to do that thing? That CEO, there are a lot of physical method. Of course, chemist is a chemical engineer practically. So he's taking the chemicals, and there are a lot of parameter also. What parameter I can say? Some of the parameter, that is delta H, solubility, delta H in enthalpy, and that is calorimetric measurements, solubility, that phase equilibria is very, very important. Solubility also very, very important. There are 8 to 10 parameters they study with that chemicals, and some ionic liquid they are using for the separation purpose, and they see which ionic liquid is more appropriate for the separation chemical, and then give the feedback to the industries people and take the money from the industries people. This is that thing. It's not so easy. That industry is also investing money for the separation to purify the chemicals to get 99%. So this is the thing is that that's why we are because industrial people in India not investing money for their industrial for their purification purpose. Suppose I'm telling water alcohol, if it is mixture is there, that you, at the eutectic point, you cannot separate water at the thing. You can get maybe 98%. But iron liquid, if you use that separation, then it can give 99 or 99.9% pure ethanol. I'm telling these things. This is the technology. This is the technology actually that we have to spend money for the separation. So anyhow, that is for paint industry cleaning agent, process chemical metal treatment cleaning, yeah, as an electrolyte in battery and capacitor. This part I told you that we have to use ionic as an electrolyte in lithium-ion batteries. To pure ion conducting polymers, synthetic polymers, cellulose, rubber. This one, lot of work is going on. And this one also extraction of cellulose biopolymer from biomass using ionic liquids. So biomass is cellulose को extract करना, biopolymer को extract करना ionic liquid as a media using. And a high order structure of enzyme generally called protein can be kept by dissolving them in ionic for the further applications. Another thing is also can be used as non-aqueous biofuel cell. This is very, very important. And that I told you, nanoparticle synthesis in ionic liquid. That is also ionic is good media to synthesize nanoparticle. These are some of the field is going on. Anyway, this is I'm telling what you do practically. Industry people what they do. Industry people what they do. Just a minute. Choice of cation that I told you. Choice of cation, anion, physical properties you can change, chemical properties you can change, and unique physical and chemical properties make them suitable for us for various chemical industrial like the suitability of ionic liquid as intertended for various separation problem. If you want to separate aliphatic to aromatic, suppose, then you have to use that is separation problem. But ionic liquid can separate. You can separate 99% alkene, ethanol. That I told you, ethanol water. We are doing even ionic liquid use करके ethanol 99.9% purity you can get it. So this is the you have to invest the money. This is very, very important because industrial people they are investing. If you say Sigma or if you say Elrich, if you say Mod, they are investing money for this maximum amount of money they are investing for the separation technology. So what is happening practically? Let's see AB reactant, that preparation, that reaction. Yeah, the reaction gives separation here. You can get the product. If it is a byproduct, and byproduct is a problem, of course, environmentally. And if we recycle AB again, then we can get it here. This is the you can say chemical plant what they do. Reaction करके जो product तो बन गया, product to how to separate, how to purify, how to get the highest purity of the chemicals. This is very, very significant, I'm telling. So this is the things, how much money they are investing. Let's see how much money they are investing. You see, a reactor can be considered the heart core of the chemical plant. Often 60 to 80% of the total cost, again I'm telling 60 to 80% of the total cost are caused by the separation step. You see a chemicals का प्रिपरेशन का जितना कॉस्ट नहीं लगता उससे ज़्यादा कॉस्ट लगता है उसको प्योरिटी को उसको प्यूरिफाई करने के लिए. So this is a very, very important thing. 60 to 80% cost used by the separation step. So where the various thermal separation process in chemical most often distillation are applied to obtain product with the dry purity to recycle unconverted reactant AB and to remove the undesired side product EF that actually show you. All these require reliable knowledge of the phase equilibrium. I told you before, this is very, very important because phase equilibrium, liquid solid, solid liquid, liquid vapor, that equilibrium study is very, very important to purify the chemicals to get the maximum purity as a function of temperature, pressure, composition of the system to be separated. So I'm telling not only phase equilibrium, there are other parameters, physical parameter. If I say to that is calorimetric measurement, that is also solubility measurements, that is also GC measurements. I'm telling very interesting things here. I want to say in Germany. They have iron liquid, they have PPR, of course. Once they prepare that iron liquid, they are using month after month. How they are using same iron liquid they are using because for the purpose, I mean, different researchers using that same iron liquid, but you can say that will be contamination procedure. No. This is the things is their end product. They are getting the product and that side iron liquid acts as a catalyst. They remain additives as the final product. They are taking that iron liquid again and they purify it. Of course, they purify it. Again, they are using that for other purpose. So this is the things is that once they prepare the iron liquid, they are using month by month, but different research scholar to different research scholars. So you see the situation. Their purification system is very, very good. Although. So anyway, understanding the behavior of iron liquid in aqueous, non-aqueous media can be avoided. They are potentially used for various physical purposes. So that is the things is there. Another key issue. I'm talking until now that iron liquid is a good one. No, there are some issues also we have to cover up. The scaling of iron liquid synthesis. I told you, quality and price are the three factors. I told you last time, if you 10 ml iron liquid, any iron liquid, maybe 10,000 cost. Quality-wise, commercial is also not good because longer period of time, that is possibility for contamination. Generally, hygroscopic water contamination is very, very significant. Then price, if you prepare in your lab, maybe 1,000 to 2,000 in place of 10,000 cost in commercially. You see the situation. Cost and quality, if you prepare in your lab, cost-wise, quality-wise is also very better. Okay. Another thing is also toxicity. That is also very the issue is that because if the chemicals is toxic, that means it's not good for use. But there is no general data available about the toxicity behavior of all iron RTIL available. Toxicity data not available to that very people are working, but not too much progress. Database of physicochemical properties that is there in Poland and Germany. They have prepared database in the sense if you want to get they have the software. If you want to you have prepared some chemicals, iron liquids. You don't know the viscosity, what is the viscosity or what is other parameters, surface tension or the conductivity values. but they have the software. You go, if you get that software, you put it, then you can get the data of that chemicals, of that ion liquid. You can get work work in the whole world, and what are the data available. You can get everything of the physicochemical properties of that ion liquid from the database software. Maybe you can get all the, maybe that chemicals, that ion liquids, database, software base, you can click it and it will give data who work, and also paper wise also. किस पेपर में viscosity है, किस पेपर में surface tension है, किस पेपर conductivity data है, they will tell you, and they have the data. They have the data also, conductivity data, surface tension data, or you can say fluorescence data. You can get it from that software. So what will help with that thing? That is very important. From that properties, you can think for the futures, what to do. That is, what application use that chemical. If you know the physical data, and for future application point of view is very, very important. Another thing, model for prediction of physical chemical properties, and liquid state molecular dynamics polarity is also very important. Another thing is your biodegradability is also very point of concern also, whether all the ion liquid is biodegradable. No, this is not like that. Recyclability, not all the ion liquid not recyclable. Some of the ion liquid I told you, they are very, very unstable. This is a problem also, but immediately based ion liquid is recyclable. So anyway, these are the key issues still now we have to address. Mainly toxicity is very, very important. Another is biodegradability is also very, very important. So quality and price you can solve if you prepare in your lab. That's not a problem. So another things, let's see. This is our research area. What we are doing now, that is ion liquid surfactant colloid interface science we are working. Another thing is polyelectrolyte ion liquid lithium salt, that is the lithium ion batteries. Another thing is drugs in ion liquid, drug delivery system, because it is very important, because ion liquid form and assemble drug entrap inside that micelle. So once it entraps inside the micelle of ion liquids, then it will open at the target point. During the flow of the drugs, it will not break. So this is also another time. Also, we are working a little bit this one. Another thing, amino acid ion liquid or saccharide, these are also working. But solution thermogenicity is old work we have done, but not now. Electrochemistry also we have done a lot in past. So mainly we are in polyelectrolyte in ion liquids with lithium, others so drug in ion liquid and ion liquid surfactants. So these are the things I'm telling in our field of research at present. Anyway, this is the last one. Thank you very much for listening, for your patience. Thank you to all of you.